Swayam Prabha. Digital India. Educated India.
What are the different kinds of smart materials are available, and how are we going to characterize the materials for that. So, probably in the few lectures, the previous lectures, you would have been discussed about the dynamics and the structural conditions, and also looked into how you can write these equations so and so. But when you are talking about any structures, it is made up of with X or Y material for that one. Okay. So, the idea is what kind of a material and why we need to use that material. That is the thing which is pretty important for us to understand that. Suppose I want something to control the vibrations. Can I use steel or copper or iron or wood? The answer is no. We cannot use that one because it does not have a special property for that. So, something like when we classify some of the materials as a smart material, what is the difference between the classical material and the smart material? We will start from there and then we will see few smart materials. So, similar, what is happening when we talk about the classical materials. So, this may do only one job. For example, if you have this structure, it is made up of with the concrete and RCC and so on. So, this will mainly use to transfer the load, mechanical load from one place to the another place, and it is a shelter for us. But there are some materials which might do much more than that, more than one job, then we call these materials are called the smart materials for this. Okay. So, typically means a person not only studying we call as a smart fellow or smart person. So, should be in in a sports and other activities, then we call that one he is the person who is going to be a smart than the other X or Y. Similarly, here also there are some materials which have something more than that what we are expecting, then these materials are called as the smart materials for that one. Okay. So, given here it is if you talk about here, and if you see here there is an input and there is an output, all the materials are going to give if you are this is made up of with some X or Y material. When I apply a force, this will displace, or if I restrict that one, this will try to generate the reaction forces to my hand for this one. So, there is an input, there is an output, but what else more than that? So, there are some materials which will give one domain and try to get the other domain for this. So, that kind of a materials which we call as the smart materials for this. All the materials you will have input, it will also provide the output, but there are some materials are specific to some applications. So, based on that one we classify ourselves, like the first one is like, in other words, some materials can be classified depends upon multi-physics problem for that one. So, what it is happening, suppose I take a steel, I heat it, it will expand, but it is not going to be significantly expand for that one. There are some material when you are trying to heat it, this will try to come back to the original stage. That kind of materials will be different than what we are using a classical material for this one. So, typical example for thermal field, some of you might be aware of this one. Have you heard about the shape memory alloys? So, shape memory alloys which is working on thermomechanical configurations for that one. So, the typical example is a shape memory alloys for the braces, what we use that one. Okay. So, how the braces are operating this one means, if you see here in shape memory alloy there are different materials are available. One of the material is the nitinol. So, what is happening, suppose when you go to the doctors, when you want to make a braces, first they do the measurements, and then what is happening, they try to put braces, means a steel, not a steel, it is a nitinol rod, small wires, they will be tightening that. And what it is going to happen, see if you put it, it has to apply a pressure to our tooth to go back to the flat stage. So, it cannot happen like 6 months once or 1 year once, it has to happen slowly. So, that is why the doctors used to say, once they put the braces, after a month they will ask you to come, then they will tighten slowly, then they tighten slowly. What it is happening basically? So, if the teeth is something like this, we wanted to make it flat. So, what happened, there should be always a pressure should be applied for this one. Are you okay? So, how do you apply the pressure? So, mechanically if you apply the pressure, it will be very, very difficult for this one. It will also be a painful job. But is there any other way we can do this one? For that reason, this kind of shape memory alloys used. The name itself will give you an idea, shape memory alloys. So, what it is happening when when all of us we try to train that particular material, take a nitinol, you can train. Train means for example, it has to expand for 10 millimeter. So, what I do this one, first I heat the material and train the material for 10 millimeter. Then after I make it 10 millimeter, I am going to expand that. Okay. So, once I produce the material will be given to you. So, it will be like a 10 millimeter rod. What I am going to do, I am going to expand it mechanically. After I expand that one, it is going from 10 millimeter to 15 millimeter. Let us take this one. It will hold in the same 15 millimeter. But what you are going to do, when you are going to heat that material, it remembers the old shape, which is a train shape, and it will try to go back to the original stage. What do you mean by that one? This will go back to 10 millimeter. You have expanded there, and then when you are heating it, it will go back to the original stage for this one. Are you okay? So, first I train the material based on my requirements, then I mechanically try to apply the force to expand or bend it, whatever you want. Then you heat that material. When you are heating it, it will go back to the original stage. So, what doctors used to do? The doctors used to first train that particular braces in such a way that it will be in expansion stage, or they will make it with based on the half perimeter, they try to make it, and then suppose it has to be some 10 millimeter half and pi by d, whatever the value if you give that one, they will put a small pieces. It is not a complete package for this one. What is happening? The doctors will try to tighten. When they are trying to braces tighten, what will happen? It will try to expand this one. After they fix it, it has to heat. When you have to heat that material, if you are heating it, it will try to go back to the original stage for this one. So, how the heating is happening? Our body temperature itself will make the system to heat for this one. That is the way how the shape memory alloy is used for the braces for this one. Are you okay? So, another example is like our stent which people are using in this angioplasty. So, you can see here there are many materials are available. Initially it started off with the shape memory alloys for this one. So, what it is going to happen? We would have been played if you have a hose and the water is flowing on this fan. If you put your foot on the hose, what will happen? The pressure will increase the other side. That is exactly happening in the artery, that one you will have a clot. So, the pressure will keep on changing that one, that will pump, the pumping capacity of heart will change. So, what we have to do, if locally this is the dia is reduced, one of the option is you increase the dia, so that local diameter can be equivalent to the other diameters in your artery in the hose, so that you do not have any problem with the blood flow. So, in that case what we have to do, we have to locally expand that artery or the blood vessel for this one. What doctors used to do? Doctors used to take this the stent inside that particular place, and the stent is something like our pen is there, ballpoint pen. When you are applying the pressure inside, you will see this, there is a ring, there is a spiral spring. Similarly, there will be a spring with a different configuration. They take it to the particular place and they expand it and then hold in that particular place, and then the catheter will come out from this one. But what it is going to happen, once it is expand, it should hold in the same position, it should not compress back to the old positions for this one. For example, if it is like something like a 10 millimeter is the dia, I cannot take this, they will take it from thighs, all along the way they take this small stent to that particular place. But what is happening, locally the dia is reduced. So, suppose you say this one, all the other places the artery dia is 10 mm, locally it is reduced to 8 millimeter. So, what should I do? I have to make it to 12 millimeter, because 2 millimeter is your dia where some clot is there, means some fat would have been accumulated. If I expand it to 12 millimeters, then inside the cross sections will be uniformly 10 mm for that one, that is an idea. So, but when you are taking this particular place, I cannot take 12 millimeter dia all along the way, because all the other places only 10 mm dia. So, when you are pushing this one, it will rupture the entire, so whatever you are having this artery. So, they do not do this one. What will happen? It will be compressed and it will easily go inside that place, and once you place it, they will expand it. and expand it whatever dimensions you want, and then the catheter will come out. But the problem is, after you are making an expansion, you should hold in the same positions for this one. What will happen? The body temperature will make sure to hold in the same positions for this one. So, it remembers the old shape, it will try to go back to the old shape for this one. That is called this shape memory effect. In shape memory alloy, one of them is called a shape memory effect. Shape memory effect means, you can make the material to go back to the original stage by applying an external temperature. That is an idea. The other configuration in the same shape memory alloys is called super elastic effect for this. It is like a Superman. So, what is the super elastic effect? Some of you would have been seen this one when you buy these specs. People used to say they rotate by 360 degrees and leave it, it will come back to the original stage, like all these connections. That is made up of with shape memory alloys. It is called super elastic effect. You rotate by 360 degrees, you apply a large deformation and you expand it and you leave it, it will try to come back to the original stage for this one. This is the two effects which will be extensively used as a shape memory alloy for an applications point of view. For example, if you suppose we take this one on a simple example in dynamics perspective. If you talk about this one, suppose I want the morphing of wing. So, when we want to change the wing morphing in dynamics perspective, what I could do, I could put this shape memory alloy as a wire, and then I can heat this shape memory alloy as a wire by applying a current. So, what is going to happen? It will try to expand or it will try to contract. So, what will happen when you are connecting this? You take as a cantilever beam and I put a shape, and there is an extension, and here I connect with the shape memory alloy. So, I am heating it. When I am heating it, what will happen? This I tune that material that it will try to go back to the original stage. Original stage is under contraction. When it is going to contract, what will happen? This will try to pull. When you are trying to pull, what will happen? This particular cantilever beam arrangement, it will try to bend. So, this is the example which you are talking about, that one. So, like when you are having the wing morphing, if you want to do, shape memory alloy could be one of the material which can be used under the shape memory effects, not super elastic effect, shape memory effect, this one. So, typically, like if I want to pull this one, I need to know what is the load which is necessary to pull that one. So, what is happening if it is like 1 feet, but I want to bend it. So, I have to do the theoretical calculation and see this one. In order to bend by this angle to be at 10 degrees, it has to pull by this much force, and this has to contract from 1 feet to 0.75 feet. I am just giving an idea. So, first I make the shape memory alloy for 0.75 feet, then I pull it. I expand it to 1 feet and then I connect it. But when I am going to heat that, how do I get? I pass a current to this one. Then this will try to go back to the original stage. The original stage is going to be a 0.75 feet. So, when it is going to shrink, what will happen? This will try to pull this one. So, that is the way this wing will go up and down direction. So, you have to put a different shape memory alloys in top and bottom to make it to go 1 or 2 different directions for this. And this is one of the example how this material will be used for some application from dynamic perspective for this one. Okay, this is what we are talking about, this thermal fields. One of the example for the thermal field is the shape memory alloys for this one. The next one we are talking about this magnetic field. So, before we take it to magnetic field, the other domain is called electrical domain for this one. So, we will come to this magnetic domain little later. So, thermal field we have given example, now we are going to have an electrical field for this one. When you talk about this electric field, Professor Littak would have been talked about, like there are some materials which can be used as a sensor and it could be also used as an actuators for this one. There is one material which can do both, right. So, one of the typical example for a material which can use as a sensor and as well as an actuators, that is called piezoelectric material for this one. So, piezoelectric material, there are different compositions like a piezoelectric material, electrostatic materials. Among that one, piezoelectric materials can be extensively used for using in order to use as a sensor or as an actuators for that one. So, typically when you look into the piezoelectric material, I simply write the linear equation. Simply if you write materials, if I have stress and I have the strain, it will be connected with respect to the constitutive relation for this one. For example, any material, if I take this particular pen, I try to apply a force, there will be a deformation, force versus the displacement. So, we do the test, we put a displacement with respect to the force, and there may be a linear and it may change non-linear for this one. And from here, what we try to change, we from force we calculate the stress, from the displacement we calculate the strain. And what is happening in the linear region, if I take this is the linear region, let us take this one, the slope of this one, it is a material property. What is this material property? Young's modulus or elastic modulus for this one. It is a simple one dimensional case. Suppose you expand that one for a 2D and 3D, we put like is like a stiffness matrix for this one. So, stress is related to the strain by using the stiffness matrix for this one. This is perfectly alright, any material, any kind of a material will have, this is purely a mechanical domain for this one. Suppose I take the other material called dielectric material. So, suppose if I want to write the material property for a dielectric material, what is happening this, you might have like this is like you apply the electric field and it will produce a dielectric displacement. This is a dielectric material. So, apply the electric field and you are trying to get the dielectric displacement. So, when you are doing this one, there should be something relating between the electric field and electrical displacement or accumulated charge per volume, whatever you call. What is this property? This is like kappa, dielectric permittivity. See, you are relating, this is, remember this is pure mechanical, I am talking about pure mechanical. Here I am talking about pure electrical. If you take any dielectric material or anything on capacitors, which is made up of with the dielectric material, what it is going to happen this one, you apply the electric field. What do you mean by electric field? You take a material, you have positive and negative electrodes, you apply the voltage. Volt per distance will give you the electric potential or gradient of electric potential, that should be equal to the electric field. So, electric field is nothing but volt per millimeter or volt per meter, that is a unit which you will be having this one. You apply the electric field on a particular dielectric material, you measure the dielectric displacement. It is like you apply the strain, you apply this, you measure the stress. Similarly, in electrical domain, you apply the electric field and you try to get the electrical displacement, or it is called dielectric displacement. There is a property of the material which plays a role, that is called kappa, it is called dielectric permittivity. So, a material will have mechanical separately, a material will have the dielectric property separately for this one. If I take wood, the dielectric property will be almost negligible, it will have only a mechanical component for this. But what it is going to happen, when we try to add something along with this one, plus will be there something. So, you are applying this this is the electrical input and you are also getting an electrical output. Here you are applying a mechanical input and you are getting the mechanical output for this one. So, I write it here, input and output. For mechanical domain, input is like a strain and output is a stress. It is not necessary input is to be strain, you can also apply stress and you can also calculate the strain. At this moment we will keep as it is. For electrical domain, we are having input is electric field and the dielectric displacement is the output for this one. And what is the property? The relations between this one will be given like stiffness matrix here. This is like a dielectric permittivity of this particular material of our interest. Now, what it is happening, if suppose I want to tell there is a material which is a piezoelectric material, if I call that material is a smart material, that material will also be a pure mechanical domain. This piezoelectric is also a dielectric material, but this will act for one combination, this will act for another combination. But what we want both together. So, which means that one, if you see in the highways, I do not want the highways for single way, I want the highway should be both lane, means both the side, two ways it should be there. So, which means that one, as an example, like we want to use this material as a sensor as well as actuator, that is an idea for that one. So, what it is going to happen, here there will be something like I apply the electric field and still you get the mechanical. This is a cross. This is pure mechanical, this is pure electrical. But if I am applying an electric field, I should get the mechanical output. Are you okay? Any questions? Any questions? Similarly, when I apply mechanical strain or a stress, I should get the dielectric displacement for this one. So, this is what you are talking about, this cross bar for this one. So, I am applying an electrical input and I am trying to get a mechanical output for this one. This is what you would have been studied like piezoelectric coupling coefficient or electromechanical coupling coefficients, depends upon the material for this one. And similarly here, it can be stress or it can be a strain. Here, this will be a D transpose. You are applying mechanical input and you are trying to get the electrical output for this one. So, this is a cross. With respect to mechanical, you are getting electrical. With respect to electrical, you are getting the mechanical, vice versa for this one. So, this is what make this particular material to be a special material or as well as called as a smart material for this one. Are you okay? So, this D and D transpose, it is called as piezoelectric coupling coefficient for piezoelectric material for this one. And why it is important? A simple example, suppose I have a cantilever beam and the cantilever beam is subjected to a vibrations. So, okay. So, what it is going to happen simply, if this is going to vibrate, simply I am putting these vibrations for this one. First of all, I need to measure, I need to sense what is the vibrations or what is the deflections which is happening in my structure of our interest. So, what is the material will you use as a sensor? There are so many sensors are available. I can use piezoelectric material as a sensor for this one. So, what is going to happen if suppose I paste here the piezoelectric material, I am just giving an idea. I mean, if you are pasting piezoelectric material, what is happening? When you are, it is going to vibrate for this one, there will be a mechanical load. This mechanical load will be transferred to the piezoelectric material. When piezoelectric material is subjected to a mechanical load, means like a strain or a stress, what is the output will you be getting here? Electrical output. So, what is your electrical output? It will be charge, or you can also measure as a function of voltage. Means I am writing a simple basic equations, but you can get many output for this one. The simplest one is it is subjected to a mechanical input, it will try to give you a electrical output for this one. So, I will take it out the sensor output. Probably what will I do? I put it out inside the controller. For this controller, this input will be given for this one. And after this controller, you may use some amplifier and so on so. And then I try to put one more piezo material. Where do we need to put? How do you put this one? That is a different story. We are not talking about this. Here we are trying to look into what is the importance of these special materials. So, here what I am going to do? I am going to apply a voltage. When I am going to apply the voltage, what will be your output? Actuation is an output. Actuation means it will try to give a mechanical output for this one. So, this is going to deflect, but the mechanical load may not allow them to deflect. It will try to reduce the deflections for this one. So, the input for this one is going to be a voltage, the output will be mechanical output for this one. So, here it is going to be an actuator. So, the same material will use as a sensor as well as the same material will also act as a, are you okay? Any questions or any doubt? So, you can, I repeat once again, I use the same piezoelectric material and this piezoelectric material will be subjected to a mechanical input and it will produce an electrical output. So, input is mechanical and output is an electrical for this one. This relation will help you and this is like it will act as a sensor. And I want to use the same material as an actuator. What should be the input? The input should be an electrical input and it will give you a mechanical output is this one. So, which means that one this will actuate, it will also act as a sensor for this one. Okay. So, that is why this material is called as the smart material for this one. Any questions? Any questions? So, there are materials like electrostrictive materials are available, but piezoelectric materials are well established and we have been using a lot, means most of the research community for dynamic perspective will be using the piezoelectric material for this one. So, the objective is when you want to when you want to identify the characterization of the smart materials, particularly for piezoelectric material, our requirement is C, kappa and D. So, if you look into this one, this is a mechanical property, this is going to be a dielectric property, but for us, when you want to use this material for dynamical applications, we don't, we may not be bothered much about this one, rather we will be bothering about this D, which is nothing but the piezoelectric coupling coefficient for this one. The name itself will give you piezoelectric coupling coefficient. In other way, in electrostatic materials, it is called as electromechanical coupling coefficient for that one. So, when you talk about this particular D, how do we need to do the measurement? Some of you would have been done the work, or some of you, when you are doing this one, you will try to put D33 value, D31 value, D15 value, that you will be placing in your and multiphysics software, or when you derive these equations, you will be using these material properties. How do you get these material properties for that one? That is one part of this one. So, typically what it is happening, when you are going to characterize the material, those who are working, some of you might be knowing D33, D15 and D31. There are, this is, these are all coming from here, this D only it is coming from here, but what is the speciality about D33, D31 and D15? So, what it is happening, the materials are considered to be like, in general materials are considered to be isotropic in nature, okay. So, steel, copper, aluminum, all are considered to be like in isotropic in nature. What do you mean by that? Any direction, if I take a sample from a bigger block, do the test, I will get only one Young's modulus, like this graph, what we are showing this one. So, it is very simple, I have a block, I cut the sample in any different directions and put it out load versus displacement and plot that, I will be getting the same Young's modulus, then it is called isotropic in nature. There are some material, when you cut in x, y, z direction and do the test, you will get the 3 different Young's modulus and 3 different Poisson's ratio and 3 different shear modulus for this one. It is called 9 constants, if you need that, that is called orthotropic in nature. I do not want to go in detail, but I am just giving few words for that one. And there are some materials which is called anisotropy, which means that one you need 21 constants for that one. But this piezoelectric material, it falls between both, like an isotropic and orthotropic. So, isotropic is 2 constants you need, one is Young's modulus, the other one is the Poisson's ratio for this one. Because one dimensional, it is only Young's modulus. What is happening? You take a steel rod, you are trying to pull, what is happening? There will be an expansion, the other directions you will have a contractions. How do you measure that one? That is called Poisson's ratio. So, 2 constants you need for isotropic. If you go for orthotropic, you need 9 constants, means 3 Young's modulus in 3 directions, 3 shear modulus in 3 directions and 3 Poisson's ratio. One could argue that one, sir, why do not you have shear modulus for isotropic material? Because shear modulus in isotropic material, it is not it is not an independent quantity, it is a dependent quantity of Young's modulus and Poisson's ratio for them. Henceforth, it is not 3, it is going to be only 2. But if you take orthotropic, you have 9 constants and 2 constants. This piezoelectric material, it falls in between that. It is called transversely isotropic in nature for this one, which means that I need 5 constants. What do you mean by transversely isotropic? I have a plane, in a plane I will have the same material property, perpendicular to that one you will have a different material property for this one. The typical example for transversely isotropic is wood. If you take a wood, if you cut it along the fiber directions, you will have one material property, perpendicular to the fiber directions you will have the other property, and if you cut it the wood and then across the stem you will have one property, perpendicular to that one another property for it, which means that one in xy plane, let us consider the xy plane, you have the same material property, perpendicular to that plane you have a different material property. This is called transversely isotropic. Are you okay? So, for that you need 5 constants for this one. In the similar sense, this piezoelectric material is a transversely isotropic in nature. So, this piezoelectric coupling coefficient, you need to have 3 values only. So, D33, D31 and D15. So, what do you mean by D33? What do you mean by D31? What do you mean by D15? If you take D33, most of the time we will be using for application D33 only. So, that is why anything if you are doing for any dynamic analysis, anything on sensor, you are using actuators or you are using in energy harvest, we prefer to have D33. So, what do you mean by that? D33 means along the direction 3. So, you apply a mechanical load along the direction 3, you get the electrical output is also along the direction 3, or you apply the electrical load along the direction 3 and get the mechanical output also along the direction 3 for this one. So, input is also direction 3, output is also in the direction 3, that is called D33 constant for this one. Okay. So, this is what it is. When you go for D31, so we apply the load in direction 1, but you get the output in direction 3, that is why it is called D31 for this one, which means that I take a block, I apply a mechanical load along the x directions, but I measure the output along the direction z directions for this one, or I put a voltage along the x directions, but output of mechanical I measure in the other directions, z directions. So, that is what it is called D31 for this one. And D15 is basically, phi means shear, we apply the force or load in the shear directions and measure the electrical output in the x directions or vice versa for this one. So, D15 is generally basically this material, piezoelectric material, this is pretty good with when you are having D15. Somebody would have been seen that one suppose the aircraft is flying and then when landing in a cold countries, icing will form. So, de-icing is one of the major phenomena. When you do the de-icing, people used to put lot of chemicals. The other way around, people also try to make small piezo patches and then try to place in this one. This will apply D15, it will cut the ice. So, for de-icing phenomena, this D15 will be used. Piezo stack actuators with D15, you have to make an arrangement of the structure in such a way that one it should operate with the D15 conditions for that one. And D31 and D33, for example, suppose you talk about, Professor Littak might be talking later or he would have talked about the extension of this work, a piezoelectric material extension is called macro fiber composites, MFC. So, what is this one? And the basic idea is piezoelectric material are brittle in nature, it is not a ductile. So, what it is going to happen when it is a brittle, concrete is a brittle in nature. In order to increase the ductility, we are putting the rods inside that RCC structure. Similarly, piezo material is brittle in nature. Under compression, it will work very well, but when you are trying to pull, it will fail. Under tensile, it will not take too much of load for this one. So, if you see most of the time, for example, people are talking about now vibration isolators for any SEM, TEM, the setups, they use a piezo stack actuators for that one. So, because number one, it is very precise. Number two, the response in nanoseconds for that one. So, that is why piezoelectric materials are used for this one. We call as a bulk material for this one. When you have the bulk material, what it is going to happen? Under the compression, it will work very well. In fact, there are some people they are doing some research like in such a way that when the missile launching, in the launch pad, they try to put this particular piezo stack and then when it is trying to take off, this will give you a reverse force. That force can be converted into a voltage for that one. But there is an analogy because voltage will be very, very high, but the current will be very, 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 very low for that one. So, sometimes when you do experiments in the lab, we will be getting a very high current, very high voltage for when it is subjected to a mechanical load. But voltage is very, very less. So, it is not going to hurt us. You can expect that one if you take a 10 mm stack, 10 mm piece jetty and when you are putting in your UTM machine, you apply the mechanical load for this one, you will get a very high voltage for that one, but it is not going to hurt us because the current is pretty less for that one. So, under the tensile, it may not work well, under the compression, it may work well for this one. In fact, today, many actuators like hydraulic, pneumatic actuators are available, hydraulic actuators are available. People are trying to for smaller load and I mean the force is very high, but if you want to have one of the other problem or limitation of this piezo material, the strain or displacement is very, very less. Force is very high, blocking force, but the strain or displacement is very, very low. Suppose we want to do a fatigue study on a biological sample. What do you mean by this? One simple example, like we are placing a crown. We want to know how many cycles when you are biting that one, it will withstand 5 years, 10 years warranty they give. For that, what the people used to do, the people used to put, because the deformation is very less, because our crown are made up of its ceramic, is also a brittle material for this one. So, when you do the fatigue study, they do not go for a bigger machine, they simply put a piezo stack actuators and apply a force on that one, like this. So, small stack actuators are available with piezoelectric material that can act as a good actuator, but very good blocking force, but very less mechanical strain or displacement, but it will work mainly on compression. There are some places where it has to be subjected to a tensile load also. That is the reason why macrofiber composites come into the picture. Macrofiber composite is something like, small piezoelectric materials are kept parallel to each other and it will be connected in between by using the epoxy kind of a material. It is like a cycle chain. Our bicycle chain, small pieces are connected and which will be flexible to rotate one over the other. This macrofiber composites like that, small piezo patches will be kept in between epoxy material will, when it is trying to bend like this, piezo may not fail or piezo may not take the load, but in between whatever we have given the epoxy flexible material or ductile material, I would say, that will take the load for this one. So, it can be a flexible in nature. If you take a pure piezo 0.25 millimeter of a very bulk piezo, if you take in your hand and you put it out nearer to the fan, it will break. So brittle in nature if you keep on reducing the thickness for this one. But rather if you are using macrofiber composites, it does not break for this one. So nowadays macrofiber composites are used. Why I am talking about this? In macrofiber composites, there are two options. One is like D33 and D31. If some of you are working or going to work, you can see macrofiber composites will be available with two category. One is like D33, the another one is like a D31. So which means that one you can apply the voltage in direction 1, you can get the mechanical strain or mechanical force in direction 3, or you can go for D33 macrofiber composite, wherein you apply the mechanical load or electrical load in direction 3, you can also get similarly at the same directions for this one. So in order to get this one, this will have its own benefits, this will have another benefits for this one. But anything you want to shear, you want to cut shear, D15 will be used for this one. So the characterization of D33, D31 and D15, this is a major challenges which we will be facing this one. There are something like piezo test meters are available, or you have to identify. See what is happening generally in mechanical materials, we do not want to operate nearer to the resonance. What will happen when you operate anything nearer to the resonance, it will fail. But for this kind of a smart material, in order to get the material property, we operate nearer to the resonance and anti-resonance frequency, then we try to get the frequency from there by using impedance analyzer, and there is a standards are available to do the theoretical calculations. This will give you all the material property what you want. I mean C, D and kappa, all these things by using impedance analyzer we should be able to measure some frequency informations, from that we should be able to calculate for this. So the characterization is very important when you want to place inside in a dynamics, or whether you want to work on something on energy harvesters, whatever you do this one. We might be knowing that one directly in the literature D33 value is given and so on so, but when you do the measurements you will be getting a different values what you are getting that one. That is always a major challenges for this one, number one. Number two, it is also a function of a temperature, right. So one of the challenges of this piezoelectric material, you can operate up to 300 or 350 degrees Celsius. You cannot go more than 350 degrees Celsius, because that material will lose out this piezoelectric concept. It will act as a normal material for this one. So there are some like Mercedes-Benz and like in a big automotive companies, they were trying to use this piezoelectric material for some applications, like even today if you see this one, now people are moving towards EV, but if you take IC engine based vehicles, this fuel injector piezo stack actuator based fuel injectors also available for that one. And similarly, what is happening, even to reduce the vibration inside the cabin, there were some attempt to make this one, putting these smart materials and see whether we can reduce this one. The other objective is like when you apply the brake, you will get a low frequency vibrations, it is called brake squeal. It is a low frequency noise. I mean, this is a very low noise because very costly cars, people doesn't like to, when you apply the brake, they don't want to listen to the noise. So, in the brake pad, there are some researches is going on that one, can we put this particular material inside and use for reducing the low frequency vibrations for that one. But the challenge is, if you see the brake pad, the temperature when you apply the brake, it will go more than 1000 degrees Celsius per ton. So, this material may not work for this one. So, like this, there are some applications where when they want to use this one, the temperature really matters, and we need to also characterize the material not only as a function of room temperature, but how, where we wanted to use this one, that also matters for this one. Even today, there are many antennas which is used for whatever they call as a dome, like Israel dome and so on. So, they are using all this camera, all this reflectors, it is everything controlled by using the piezo stack actuators, because you can control the antennas with 0.01 degree of angle, you can control it. So, that you will get a very precise measurements or images which you can get it for this one. So, most of the time the domes are made up of with movement of the domes and reflector to change the directions depends upon the satellite and other things. Local, they will also use a hydraulic or pneumatic, but along with this one, these minor changes can be done by using the piezo stack actuators for this one. In fact, Samsung is trying to use earlier stage in the camera, mobile cameras, to get the clarity of this one inside the piezo stack actuators are there. I do not know now, probably earlier in early 2010 they tried to develop the technology. Okay. So, why I am talking more on piezo, most of the dynamics, we try to use the piezoelectric material as an extensively for an applications to get either use as a sensor or actuators or as a energy harvesters or structural health monitoring, whatever you want to get this one. And I come back to the last one, it is called a magnetic field for this one. So, the magnetic field is called, one of the example for the magnetic field is a magnetostick tube material for this one. So, magnetostick tube material is similar to piezoelectric material. So, what is happening, instead of electric field, you will have the magnetic field for this one. When you apply the magnetic field, you will get a mechanical output, and when you apply the a mechanical input, you can also get the magnetic output for this one. So, what will happen here, this one will change it to B, magnetic induction or so on so, and here E will change it to H. H is nothing but the magnetic field, and instead of D, you will have E transverse for this one. This is like a piezo-magnetic coupling coefficient or magnetomechanical coupling coefficients for that one, giving a simple idea for this. So, there also when you talk about magnetostick tube material, one of the typical magnetostick tube material is like terphenol D. And there are some compositions are also available. So, what it is going to happen, and there you apply a mechanical load, you will get a magnetic field, and the magnetic field can be measured by using some techniques of our interest. But the thing is, magnetostick tube materials are not extensively used for many applications, because when you want to develop the magnetic field, you have to put the the material inside the permanent magnets, or you have to generate a very high magnetic field for this one. So, a typical example for magnetic is MRI. So, sometimes you would have been read in the newspaper that the person who went along with the oxygen cylinder, it sucked inside the field and then got crushed for this one. So, you should not have any metals when you go for MRI, because it is 1.5 Tesla. You would have seen somewhere, or some scan centers would have been put 1.5 Tesla, 3 Tesla and so on. So, 1.5 Tesla is approximately 1500 Oersted or 3000 Oersted for this one. So, generating the magnetic field needs a lot of energy for this one. So, applying the magnetic field and getting the I know mechanical output, you need lot of energy and power. Henceforth, magnetostrictive material are not extensively preferred, rather piezo is very simple, because I put electrode, I put 2 wires and I can get this one. So, even though conceptually it is the same, but it has major challenges which you are having this one. Okay. And typically, I will stop with probably, like when you are talking about here, you can see here piezo ceramics is like piezoelectric material, and magnetostrictive material which we have discussed about this one, and shape memory alloys also we looked into that. But what it is happening, you can also do a cross combination between that one. So, typically what you can have magnetostrictive material and you can add the shape memory alloys for this one. That is called ferromagnetic shape memory alloy for this one. So, you can interface magnetic field with respect to the thermal field for this one. That kind of an interactions also we can do this particular case. However, the rest of them means the piezo ceramics and electrostrictive are linked one over the other. There are some materials which will be a lower version of electrostrictive and upper version is called piezo ceramics, because it depends upon what is happening, there is a hysteretic effect. So, if you have a hysteretic effect, then it is called piezo ceramic, or if you have very less hysteretic effect, then it is called electrostrictive for this one. But this may not be extensively used, only piezo ceramics are extensively used, because manufacturing point of view, cost perspective, strain which you are trying to get perspective, piezo is better than electrostrictive for this one. And shape memory alloys, independently shape memory alloys are also extensively used. Magnetostrictive materials are having the restrictions, except some special applications. Magnetostrictive materials are generally not extensively used for this one. If you take ferromagnetic shape memory alloy, is a combination of both for this one. Once again, this is also from theoretically or in a lab level it will be used, but when you take for an applications, really challenges, because here also you need a magnetic field. That is a challenge for this one. However, if you look into dielectric elastomers and ionic polymers, this is extension of only electromechanical coupling, but what it is going to have is, as I told you, if you take piezo as electrochemic material, if I say this one piezo ceramics, magnetostrictive material, these two are brittle in nature. Okay. So, the other restrictions for this one, the mechanical strain or displacements are pretty less. Okay. But suppose I want a large deformation, you would have been seen something like robotic, and the robots you can see this one, and the robotic arm will try to deflect a lot and try to pick the material and keep it in other places for this one. It is a large deformations. If you want to get the large deformations, what you need to do? You need to go for hydrogel, polymeric material for this one. So, henceforth the dielectric elastomers and ionic polymers, these two emulated for this one. It's basically there are a PVDF, polyvinyl difluoride, is a PVDF, it's like a thin sheet. It can go for the large deformation, it can also both, it can used, it can use, you can pull it out, it will elongate a lot and you will get an electrical output from this one for this. And you can apply the voltage and you can also make it the elongations for this one. Both it is possible in PVDF. PVDF is one kind of a dielectric elastomer. There are different varieties of elastomers are available, which is like ductile in nature. It is not brittle, it is ductile in nature. At the same time, you can get the mechanical output is large deformations for that one. And ionic polymers also similar to what we are talking about. This one is a chemical composition by which you can make it, and it will work. Ionic polymers and dielectric elastomers will work with the electromechanical coupling of our interest. The smart hydrogel, it is like it is, though it has been placed under smart materials, but this kind of hydrogels is called self-healing polymers. Self-healing polymers. So, what it is going to happen? It is like in our in our car we have when you there is an impact, this airbag will come out and then stop. It's like this. If you are using in composites, sometimes there is a crack initiated and it propagates that one, there will be a molecules which will be there. So, either based on the heat or based on the deformation, inside there will be a small pockets, that pockets will open and then that will get solidified in that one. So, it will allow it won't allow the crack to propagate, it will try to stop the crack inside that one. So, this kind of materials with smart hydrogels are available. However, among these all applications, this I would say these piezoelectric materials are extensively used for dynamics, particularly sensor and actuators, or if you want to use for health monitoring or energy harvester, so on. So, probably one of the challenges in piezoelectric is brittle in nature. The other problem which we feel this one, it is and the strain out mechanical output is pretty less. So, we try to go for something like elastomers, piezo polymers or piezo elastomers, that will try to improve the mechanical output as well as reduce the brittleness for this one. The last point which I want to say this one, all of them are okay, but there is always another restriction, that one, what is the maximum load we have to apply? What is happening? It may not be a linear. So, as we discussed about here, even if you take any material like let us say, so what is happening is a simple load versus deflection for any steel. If you do this one, after some time this will fail. Okay. It may be a linear up to some things, and then it will generate a non-linear part for this. And what is going, when you are trying to unload it, this may come like this, and then if you go ductile material, this will make something like this. In the region, it will be keep on piling. So, there is a hysteretic effect which will be seen in typical mechanical materials. Similarly, if you plot like piezoelectric material or magnetostrictive material, whatever the case, if you have electric field and if you do apply electric field and measure the dielectric displacement based on the constitutive relations what we have written here, what will happen? So, it is something like you will have a hysteretic effect for this one. So, what you will do? You will always operate only in the linear region for this one. If you go for a higher voltage, you will end up with a problem, because there is a non-linearity will be coming in this one. So, we have to operate only in the linear region, and then this will give you an output for this one. That is one of the restrictions. For example, some of you are working in these macrofiber composites. The company would have been given, there is only one company selling of macrofiber composites. They will tell that one you have to operate up to plus or minus 70 voltage, or you have to apply minus 500 to minus 70, something like that. They will give the range for this one, because this is the range only you have to operate. If you operate more than that one, there will be a non-linearity will be coming. Then you may not expect, means when you go, it is not only a non-linearity, you will get the loop. When you have the loop, what will happen? For the same load, you may get two output. There won't be any unique solutions for this one. Henceforth, we have to restrict ourselves to only the linear region at which you have to operate for this one. That is one of the problem which we will be facing, particularly with respect to this material, but still the range is very comfortable to use this one. So, there is a non-linearity involved in this material. The fabrication of the material is also a bit challenging, and also making this material to use as an actuator and sensor also. When you are buying this one, there will be one other options called polling. So, they make the material to use directly as a sensor and actuators, they will give that one, and we have to take it, otherwise we have to get, if you are preparing the sample, we have to poll it, then we have to do the characterizations for this one. So, it's a something like there is a limiting range, and there is also limiting in the temperature for this one, and on average we would prefer to go up to 200 degrees Celsius, a classical PZT. More than that, the deterioration will start in the material properties, which means that one, it started off failing as soon as possible for this. So, that is the limitation of any kind of a smart material. This is the same influence with the magnetostriction also. Only thing is, if you plot this magnetostrictive material, this will be H with respect to B. Here electric field, here is the magnetic field, and here is the dielectric displacement, here magnetic inductions. What will happen? Here also you will have hysteretic, but what is what it is happening, the hysteretic will be very less in this one. Here you will have a significant hysteretic effect, here the hysteretic effect will be less. But one of the problem in this magnetic, you have to have a good magnetic field. How do you generate the magnetic field? Either you have to place two permanent magnets, you have to place in between this one, and if you are keeping increasing thickness, the magnetic field keep reducing this one. Otherwise, you have to put the electromagnet, and you have to apply the power to generate the fields, and in between you have to place this material. So, it's really challenge to do that one. And if you want to generate very high field, if you are using a magnets will get heated up quickly. So, you have to have a chiller water you need to circulate the water inside to remove the heat which is generated inside. But in piezo that is not a problem, or in electro that is not a problem. Simply you need to have an amplifier, you just top and bottom electrodes you connect it, you should be able to get this one. That is why this material, piezo materials are quite familiar than the magnetostrictive material, except some special applications magnetostrictive materials are used. Shape memory also is used. Shape memory alloys will also have a non-linearity. So, like shape memory alloys, if you plot stress versus strain, what is going to happen? You will get the hysteresis something like that. So, you will this will also hysteretic effect, but one good thing is when you are loading and unloading, this will try to come back to the original stage. There is no permanent deformation. That is the benefit of shape memory effect for this one. So, there is like Martensite transformations and other stuff available. I do not want to go inside, but rather shape memory alloys and piezoelectric materials used. The characterization of these materials are very, very important, which will really help us when you are doing any kind of a dynamics, because based on this input we will be getting how close your experiments with your theoretical calculations or numerical calculations will be getting this one. So, it is something like you have to when you want to get this material property, and there are two things. One thing is we have to find out these VSM measurements. The other one is we have to take the material, you have to paste the strain gauge, and then you put inside the magnetic field, and you have to measure the applied field with respect to the strain, then you have to plot that. From that graph you have to get the material properties whatever you want for this.